an absolute novel because I've never heard a neuropathologist give a talk at the Nephropathy. So John Wilson probably didn't know much about kidney before he joined Arcana Labs several years ago. If you look at his CV, he's board certified about almost everything but renal pathology. His main interest now, I think, is molecular pathology, where he trained. It was somewhere a very important place, I think. I don't find it here. And neuropathology with a focus on muscle and nerves. So, looking forward to your talk, John.
Thank you very much, and thank you to the organizers for inviting me. And it is odd, I've never had the opportunity to speak at a renal meeting as a neuropathologist and a molecular pathologist. But I have to say that my job's very interesting, and in getting ready for this talk too, I learned a lot, which is actually a pretty neat thing. And hopefully some of this makes sense. And on top of that, as you had said, one of my disclaimers is that I am not a medical renal morphologist. And so my apologies, my limitation. A lot of this conference sounds like it's about precision medicine. And one of the goals of that is to make a new taxonomy or classification of disease based on molecular biology. So that's one of the undertenants. But as Dr. Barsani said too, I think it's an integration of all the information. It's a systems biology thing, and molecular is part of that. And it's the outcome of patients that you're hoping to improve. Why perform genetic testing? There's some basic reasons that you want to do it. It can be diagnostic, it can be prognostic, it can be predictive, and other. And so diagnostic, we would use in pathology to render a more definitive diagnosis. Prognostic is, how's this disease going to behave if I don't treat it? Just what's the natural course of it? And then predictive, if I treat it, what can I use? And how's it going to behave? How's the patient going to fare? And then other. Genetics, as you know, it doesn't affect just the person that you're testing. It affects the family, and relatives, and potentially communities. And and I'm going to do my talk kind of in a case base. So I'm going to introduce a case, and then I'm going to go into the molecular. And I'd like to do talks freeform, but given time limitations, we might not be able to do it on this one, but definitely come ask me or email me. So this first one is a 12-year-old African-American male, nephrotic range proteinuria, and hypertension. It's incidentally found on the school physical. And on biopsy, he shows, I was taught to say that this is focal segmental glomerulosclerosis, and that there's a little bit of hyalinosis focally. The blood vessels don't look too bad. And so we made a diagnosis of just FSGS. And in the comments suggested doing APOL1 testing because this patient was African American. And you guys have probably heard about this, and his test came back positive. So he had 2 risk variants, and that changes essentially his diagnosis to most likely being APOL1 associated nephropathy. And this is something that you've probably been hearing a lot about, and it's actually really interesting as a mechanism. And I think it was, you kind of already get a leading that something's up, and that African Americans, and I'm going to be focusing mostly on America because that's my experience, but I'll try to extend out as well. So a 4-fold increase in end-stage kidney disease, and mapping studies linked this to chromosome 22. Initially, this was thought to locate to MYH9 gene, but subsequently later was found to really belong to APOL1. And so APOL1 is one of 6 APOL proteins, and these are actually part of innate immunity, and APOL1 is the only one that's secreted. What's interesting is that it arose in West Africans. Approximately 4,000 years ago, there were some variants that arose in West Africans in APOL1. And so this gets to this idea too, it's pretty neat as far as environment influencing human biology, so evolution. And so these 2 variants, the G1, which is 2 adjacent single base pair missense variants, and G2, they both arose about that time. And they made their way to America via slave trade, the transatlantic slave trade. And so at this point in time, when you look at these variants, Why did they arise? And it's because it was a response to African sleeping sickness. So this is very much like sickle cell disease, in that you actually have variants that come up in response to an infection, although sickle cell wasn't an infection. And so these APOL1 variants actually engender resistance to infection by trypanosomiasis. And so, but that can come with some caveats. And so T. brucei is susceptible to wild-type APOL1. APOL1, again, is an innate immune molecule, and it travels along in an HDL3 complex. It's ingested. Apparently, trypanosomes like HDLs, and they go around eating them. And then what's interesting is that there's an APOL1 that's attached to that, and once it makes it into the lysosome, the acidic environment causes it to be released. And it inserts itself either into the membrane of the lysosome, and it causes swelling and death of the parasite, so trypanolysis. Over time, T. brucei probably wasn't too happy about that, so it's going to mutate, or it's going to undergo some evolution. And so it picked up resistance to APOL1 wild type with this serum resistance associated protein, SRA. And so T. brucei basically evolved into T. rhodesiense. And it is resistant to wild type APOL1. And humans, therefore, kind of in an evolutionary war, developed these two variants, G1 and G2 in APOL1 that, again, made this trypanosome sensitive to lysis. So again, it's protective. The trouble with that is that heterozygous, so if you only have one APOL1 risk variant, you get the resistance to trypanosome infection, but if you get two of them, you're at risk for renal disease on top of that. And that's kind of the basic story. And it's relatively common in African Americans. The United States, about 36% of people will have. And the variants are located in this SRA interacting domain. And what's interesting is that the two variants, this is an indel, and it's a 6 base pair indel. And these are two single base pair changes. And they never are on the same copy of the chromosome, so they're always on different alleles. And that's, so they're in perfect linkage disequilibrium. And these two are always inherited together. And this one is thought to not be necessary for pathogenicity, where this one is. So in the way that this works out is these are, in some ways, behave as an autosomal recessive type disease. You have to have both copies of the gene involved with pathogenic mutations. 10% to 15% of African Americans have 2 risk alleles, and they have a 4% lifetime risk of FSGS. So the etiology for APOL1 glomerular damage, nobody's quite sure. Lysosomal, and so they know the trypanolytic mechanisms kind of make sense, but how does it cause renal damage? And nobody's quite sure. So one of them is it lysosomal membrane permeabilization? Is it autophagic? Is it apoptosis, mitochondrial dysfunction, cellular potassium depletion, and activation of stress response? And what we don't have that answer, but what we do know is that there's a lack of nephropathy in patients with null mutations, so it's not necessary for normal function. And if you overexpress it, even the wild type in cells, it is toxic. And variants are more toxic than the wild type. And the renal disease does not correlate with serum levels of APOL1, so it's in the kidney. So it's native to the kidney this is happening. And the renal damage appears that it can be initiated by a variety of triggers. And so you can be perking along with your two variants for quite a long time, and then some things will happen to kind of trigger that damage. And so some of the things that you see in association, you can see as far as odds ratios in African Americans, the odds ratios are pretty significant. So 17 for primary FSGS, HIV-associated nephropathy, 29, so very high. And you can see increased in other diseases as well, including sickle cell. And on biopsy, patterns that you will commonly see would be FSGS in African Americans is one of the things that we use as a cue to, we should try testing this patient to see if they've got it. and if you have collapsing lesions. In our lab, what we use is a PCR assay. It's pretty sensitive, and it's also an inexpensive test, and it's pretty fast. And so that's one of the advantages of it. You can do this, we do this on renal biopsy tissue, we can do it on formalin or frozen. You can also do this on peripheral blood. And now you can imagine the other part about this is that if an African American individual has APOL1 related nephropathy and they come up for transplant, oftentimes it's a family member that's going to give them a kidney. And so you need to test the family member to see if they have two risk variants, because if it gives away a kidney or they give away a kidney, they're at increased risk as well. And so we receive biopsies or materials for testing on FSGS patients, but also living kidney donors, and we do get some on patients just wanting to know what their status is. So, any questions about APOL1? Sure.
Yeah, I have a question. I'm from Belgium, and I was just wondering what is the prevalence of the APOL1 genotype, for instance, in Central African patients? Because in our practice, we sometimes have Congolese patients, and I was just wondering, is it necessary to be tested for that as well in this population?
And I actually have to read more. I know that in the West African or Sub-Saharan African area, and my geography is bad. I grew up in Hawaii, and so it's definitely isolated. But as far as in Sub-Saharan Africa, about 46% of the people will carry the variants. And so if they have, and same thing too, African American slave trade also went through Cuba. So you've got Hispanic, and also, so if it's recent African ancestry, is the risk to kind of pay attention to. And then as far as the assay that we use is PCR, as you know, it's basically you take DNA of interest, you put a polymerase with it, you put primers that are specific, kind of bracket the area you're interested into, you melt the DNA so it separates, the primers bind, and then use a polymerase to copy it. And then you've made that copy, and then you split it again, and you do it again, and you split it again, you do it again. And after 30 to 40 cycles, you have millions and millions and millions of molecules. And then what you want to do is be able to look at the area that you're interested in. So is it mutant, or is it wild type? And so you can make a probe that's specific to that. And we use these things called fluorescence, resonance, energy transfer probes, or FRET probes. So while the DNA polymerase is copying that single molecule DNA, it will auto-digest this kind of probe, and it releases the fluorophore, which is quenched by being adjacent to a quencher. Once it's released, it fluoresces, and all we have to do is track that. And so DNA polymerase, in this sense, behaves kind of like Pac-Man and eats up this fluorescent probe and releases the fluorophore. And so we can actually track this. So if we have, say for G1, G1 is blue and wild type is red. You can see here that the G1 did come above threshold. And so this patient is homozygous wild type. This patient is heterozygous for both. And this patient is homozygous for APOL1 G1. And so it's very quick, it's inexpensive. Disadvantages of PCR is you have to actually know exactly what you're going for. You can't just blindly do a test and know that it's going to be there. So you actually have to have an assay that's developed that way. So, utility of this test, it establishes a genetic diagnosis. Prognostic, it tells you something about the risk of end-stage renal disease in various clinical contexts. It's predictive. There is no effective treatment, although there is a lot of effort going toward it. What you do know is that the disease will not recur in a transplant if you tested the patient giving the transplant and they don't have two risk events. And then the question is, other family members have risk. So this is common. Renal biopsy changes are relatively nonspecific, and that's what's actually neat about what's happening with molecular biology, is you can take something that is relatively nonspecific on morphology and find something that is more specific. And so that's pretty cool. So if you have a single risk allele, there is no increased risk. If you have two of any combination, it can be two G1s, two G2s, or you can be compound heterozygous, you have increased risk. And it's interesting, again, that it's a genetic susceptibility and an environmental trigger. This is There's many other diseases that do this, like multiple sclerosis, same kind of idea. You have a genetic susceptibility, and then based on an environmental exposure, you can develop disease. And so we basically test, if we get renal biopsies and have FSGS, we test African American patients of African ancestry. And oftentimes we'll receive sequencing. Somebody will want to do an FSGS sequencing panel, which is a much more expensive assay. And what we do first is we'll do this first and find out that it's negative, because this costs like $100 and the sequencing test is more expensive. And the precise mechanism of renal injury is unknown. Okay, so 16-year-old male admitted for acute renal failure, metabolic acidosis, and rhabdomyolysis, and radiologic examination revealed multiple renal cysts. On biopsy, you can see there's a lot of fibrosis. There is some chronic interstitial inflammation. There's some periglomerular fibrosis, which you can see better on the Jones. And so this is called chronic tubular interstitial nephropathy, severe. The patient requested testing, and so one of the more common causes of this is actually homozygous deletion of NPHP1. And so we did FISH, and it's a relatively inexpensive way to do it, and it's neat. And you can see, this is probably the best example. This is a normal. You would expect 2 NPHP1, which are red, and you would expect 2 centromeric Sept2 probes, so that's normal. And so these guys, this is a normal look. This is an abnormal patient with homozygous deletion. You can see there's no red signals. And so FISH is actually neat in the sense that you don't have to have a fancy molecular lab to do FISH, and same for PCR. And FISH, one of the strengths of FISH is that you get the genetic information, but you also get morphology. You can tell which cells it's in. And as a surgical pathologist, that comes in handy when you're dealing with cancer, but it's also nice in this setting as well. Why do you not see 2 signals, 2 red, 2 green in all the cells? It's because you're dealing, in this one, we're actually using a tissue section, and so you truncate the nuclei, you'll cut off signals, and so you have to account for that when you're doing your validation. So the diagnosis after the FISH is NPHP1 related nephropathy. And this, as I started learning more about it, feels almost like Alice in Wonderland. You kind of go down the rabbit hole and it kind of expands out. And it's pretty amazing. It's actually really, really cool. But nephron enthesis, so it's Latin from consumption, decline, or wasting away. It's the most common cause of end-stage renal disease in the first 3 decades of life, and you can categorize it based on when they go into end-stage renal disease. And so again, relatively common. Clinical, you get polyuria, growth retardation, decline of renal function during childhood or adolescence. And many cases can be renal limited, but there are also syndromic ones that are involvement outside. And so if you get liver fibrosis, one of the things you would consider would be Meckler-Gruber syndrome, cerebellar-vermis hypoplasia or aplasia, Joubert syndrome, and in retinal involvement, Senior-Loken syndrome, and then you can get some other things as well. This one is always kind of interesting, and this is kind of segues into the next section, Situs Inversus. And so what they found is that, I'll have to come back to that. These can be, the genetics of this is they are autosomal recessive, inheritance pattern, and it can be due to single nucleotide variants, so just one base pair change, or insertions and deletions. And what's interesting is that these have to do with cilia. And I didn't know a whole lot about cilia before I read this. I mean, I knew like sperm have cilia and they move around, and I didn't know a whole lot that there was this thing called primary cilium. So first, motile cilia are the ones that actually use for movement, has a 9+2 microtubule configuration, and you guys are all familiar with EM probably, and so you're very aware of this. And so depending on where you take your cross-section of the cilium, you'll see different morphologies. If you take it through the basal body, it has triplets. If you take it through the mid part of the axoneme, it'll have doublets. This one is actually at this level. If you take it through this transitional area, it'll have doublets with these Y structures. And if you take it through the mid portion of the axoneme, then you'll see the classic thing you're used to seeing, 2 to 9 doublets with dynein arms, and then 2 central microtubules. So that's for motile cilia. What's interesting is function-wise, they function in cell signaling as well as in motility. And in cell signaling, they do chemosensation and mechanosensation. When you go into non-motile cilia, I didn't know this, but most cells in the body have a single non-motile primary cilium. And it basically behaves like an antenna. So it sticks it out, and it senses the outside environment. And it has to do with cell polarity, with embryogenesis, with day-to-day functioning of that cell. And when you consider how adaptable your body is, rods and cones in your retina do this, are cilia, apparently olfactory cells also. And so again, what you've got is this sensor that sticks out. And it has different domains. So the other part about this is that, and this is where it gets, I don't know, neurologic, in that the cilia actually maintains its own internal environment. So it's almost like it has a blood-brain barrier kind of idea, in that there is this transition area that gates everything that comes into the cilia. It's very much controlled. And so, so it has to maintain that. And also, non-motile cilia have this inversion domain that has to do with signaling. So again, if you keep looking at this, proteins, because there's no machinery to make things in the cilia, it has to import everything. So things have to make it into there in order for it to function. So there's actually an intraflagellar transport system that uses dynein and also kinesin. And so there's things that can go wrong with that. The other thing that gets to be really interesting is that the basal body, which forms the base of the cilium, is actually centriole too. And so it has the mother basal body, or centriole really, and then a daughter centriole. And what's interesting is that based on cell cycle, these change places. So in G1 and S phase,